Hi, welcome to the channel Naukri Learning. My name is Kanika Garg and I have specialization in machine learning, deep learning, data science with Python. Today we focus on convolutional neural networks and how to implement them using Python for image classification. So let's talk about today's agenda. First, we will learn about convolutional neural networks and how they work. Then we talk a little about the dataset that we are going to use today for our programs. And finally, we are going to do a code on Google Collaboratory. And I think it's a great platform. It is really fast and it is suitable when you do not have the softwares installed on your machine. Talking about convolutional neural networks, I think by now you might already know about machine learning and deep learning. Computer science, these are the computer science branch that studies the designs of algorithms that can learn on their own along with the data. So deep learning is a subfield of machine learning that is inspired by artificial neural networks, which in turn are inspired by biological neural networks and specifically biological cortex. So even the convolutional neural networks are deep feed-forward artificial neural networks that are inspired by the biological cortex. And if we know that the models are called feed-forward because the information flows right through the model, and there are no feedback connections in which the outputs of the models are fed back into themselves. So, convolutional neural networks have been one of the most influential, say, innovations in the field of computer vision. They have performed a lot better than traditional computer vision and have produced state-of-art results, especially in the areas like image classification, object detection, and face recognition. So, moving forward, let's understand the data that we are going to use today, that is the fashion MNIST data. And so before we go ahead, we have to load this data, and it's good that before working upon it, let's have a good look on the data. So it is basically a data set of Zalando's article images, and they are 28 cross 28 pixel gray images of 70,000 fashion products from 10 categories. That means we have 7,000 products from each category. And for training purpose, we have used 60,000 images for training part, whereas 10,000 images we have used for the testing part. So fashion MNIST data is similar to the MNIST data set that we already know, which has handwritten digits. So that means the image dimensions, the training, and the test splits are similar to that data set only. So this is how the images look like in the data set. If you can see, there are 3 rows dedicated to each of the category. The last 3 rows are dedicated to the boots, and then to the bags, then shoes, and then t-shirts and all. So this is how our data set looks like. And these are the images of the size 28 cross 28 pixels each. So moving forward to the collaboratory notebook. Here I have pre-written some code to save us some time. So this is how a Google Collaborative notebook looks like. Here I have named it as Fashion MNIST CNN. This is the name I have given to my notebook. You can give either of the name, whatever it suits you. So these are the cells. It basically is an imitation of the Jupyter notebook. So if you are aware of the Jupyter notebook, it will be easier for you to work on Google Colab. And it is really easy to work on it, and maximum of the libraries are already loaded on it. So we really don't need to use pip statements for installing any libraries in Google Colab. Now, Keras comes with a library called datasets, which we can use to load datasets out of the box. So here we can download the data from the server, and it speeds up the process since we need no longer to have to download our data to our computer and then finally calling it from our system. So the train and the test images along with the labels are loaded and stored in the variables train X, train Y, test X, and test Y using this data. So let's start and run this cell. If the internet is slow, it will take some time for you to run the cell. So it has finally downloaded all the data. Now, what we have to do is we have to analyze the data, what data we have, what is its shape. So now let's analyze how images in the data sets look like. Even though we know the dimensions of the image by now, but it's still worth the effort to analyze it programmatically. So we are using NumPy to find out the number of classes the datasets has. And here, if you can see the training data shape, it has given as 60,000 images is the number of images, and 28 by 28 is the size of each image. Similarly, for the testing dataset, it has given us 10,000 with 28 cross 28 size image. In the next cell, we wanted to find out the unique number of labels we have. And for that, we have used NumPy. And if you can see here, the total number of outputs that we got is 10. That means we have 10 classes of images, and the output classes are numbered as from 0 to 9. So from the above output, we can infer all such information, right? So if we want to see what kind of images we have in our data set, we can just always fetch some of the data from the training data set or maybe from the test data set and get printed here. So the 10 classes that we have here are t-shirt, trouser, pullover, dress, coat, sandal, and these are all numbered from 0 to 9. Now to display how our images look in the data set, we are going to use matplotlib. And if you can see, there are two images that we got because we have printed two images, one from the training dataset and one from the testing datasets, and they both look alike. So the output of the above two plots looks like an ankle boot, and this class is assigned as a class label 9. Similarly, the other products will have different labels, but similar products will be labeled same. This means that all the 7,000 ankle boot images will have a class label of 9, like it's given here. Then let's move on to the data pre-processing part. As we can see in the above plot, the images are grayscale images and have pixel values that will range from 0 to 255 for one channel only. Since it's a grayscale image, it has only one channel. So also these images have a dimensions of 28 cross 28 pixels. So as a result, I have to pre-process the data before I can feed it to the network. So as a first step, what I'll do is I'll convert each image from training and the testing data set to a matrix of 28 into 28 into 1. 1 represents the number of channels. Since it's a grayscale, it has the value 1. And since if it was like RGB, the value here would be like 3. So let's see. After reshaping, this is the output that we got for training and then testing. The data right now is an int in the integer format. So before we feed it to the network, we have to convert it to the float, and further we have to give the values between 0 and 1. So we are just need to rescale the values from 0 to 255 to 0 to 1. So for that, first we just have converted them to the float values, and then finally divide each value by 255. So finally, we got the answer, and the values will get say rescaled in the range of 0 to 1. Now we need to convert the class labels into one hot encoding vector, so it will be easier to classify. So to change the labels from categorical to the one hot encoding, it's basically a vector of numbers. So the why we need to convert the categorical data is that the machine learning algorithms, cannot work with categorical data directly. So we need to generate some Boolean column for each category or class. Only one of these columns could take on the value 1 for each sample. Hence the term called as the one hot encoding. So for our problem statement, one hot encoding will be a row vector where for each image, it will have a dimension of 1 cross 10. The important thing to note here is that the vector consists of zeros except for the class that it represents. For that, it is 1. So let's see how we do it in our code. So we have a function called toCategorical, and using this, we can just convert our labels, categorical labels to one hot encoding. So the original label to this train y0 was 9, and after the conversion we got is this. So only the 9th label got 1, otherwise all the labels are 0. So now I think it's pretty clear that after one hot encoding, only the label, which is the actual value of it, is 1. Otherwise, all will be 0. Now, after this conversion to one hot encoded, we have to split our data carefully from training to training and validation set. This is the last step, which is very crucial. Now here, for the model to generalize well, we split the training data in two parts, one designed for training and another one for validation. In this case, we train the data using 80% of the training data, and rest of the 20% of training data will be used for validation. Now, this will also help to reduce the overfitting, since you will be validating the model on the data and it would not have seen in training phase, which will help in boosting the test performance. For that, we already have a function in sklearn model selection, that is the train and test split. We can just call that function and provide our data to it. It will help us divide the data by the size that we tell them. Here, if you see that we have given a value of 0.2, that means 20%. So what it will do is it will divide the data in the ratio of 80 and 20%. So 80% will be given to the training data and 20% will be given to the validation data. Then we can just see the shapes of all the data sets that we got after the division. Okay. Now, finally, we have worked on the data part. Now, let's come on to the network part. The images are of size 28 cross 28. Now, we convert the image matrix to an array and rescale it to 0 and 1. And then we have reshaped into 28 into 28 into 1. And then we feed this as an input to the network. So we are going to use 3 convolutional layers. The first layer will have 32 filters. Then the second layer will have 64 filters. And similarly, the third layer will have 128 filters. And similarly, with each convolutional layer, we are going to use the max pooling layer, each of size 2 cross 2. Now to do that, we have to model the data. So first, let's import all the necessary modules required to train the model. So here we have used Keras models for sequential input and model. And then for the layers, we are using dense dropout and the flatten layer. Similarly, convolutional 2D layer and the max pooling layer. And for normalization, we are using batch normalization. These are the parameters that we are setting for batch size. So we can either take the batch size of 64 or we can take the higher batch sizes also. So now that will depend on your experimental part. So here I am using 64. You can try out with 128 as well as 256 also. It also massively contributes to determining the learning parameters, and it also affects the prediction accuracy. So we can just always change the batch sizes and try out the various say accuracies we are getting. Number of classes we already know they are 20s, and epochs I'm using 20. So we can go for the lesser epochs also. And if we try, we can let's just start with 10 epochs because it will take time to learn the network. Now this is how we define the various layers. First, we define the model as a sequential model. Then we add each layer. First, we will add the convolutional layer and we provide the various parameters. The kernel size is 3 cross 3. We are using activation as linear and input shape is this. Then we are just adding the ReLU layer, then max pooling layer. Then again, since we are going to add 3 layers, so if you can count it here, 1 convolutional layer, 2 convolutional layer, and 3 convolutional layer. So this is how we are creating 3 hidden layers inside the convolutional neural networks. So let's just try and run it. I'm sorry, I forgot to run this batch. Now this. Okay, it has run successfully. Now, if you see that I have used here as leaky ReLU, so more specifically, we add these because they, attempt to fix the problems of dying rectified linear units. The ReLU activation is used a lot in neural architectures and more specifically in convolutional networks, and it has proven to be more effective than widely used logistic sigmoid functions. And also we have added max pooling layer with the convolutional neural layer. And of course, we have given the pool size of 2 cross 2 and the padding as same. Now, finally, we have a dense layer and it has a softmax activation function with 10 units, which is needed for this multi-class classification problem. And we need 10 units because we have 10 classes, separate classes, for which we wanted to divide our data. Now, after the model is created, we compile it using Adam optimizer, one of the most popular optimization technique. And we specify the loss type, which is categorical here, categorical cross entropy, which is used for multi-class classification. And we can also use binary cross entropy as a loss function also. So let's try and run this to compile our model. Okay, it has run successfully. Now let's try and visualize the layers that we have created by using the summary functions. This will show some parameters like weights and biases. These are the parameters in each layer and also the total number of parameters in the model. So now if you can see here, the number of parameters in first convolutional layer, it has is 320. Then the second has this, and so on. If you can see here, the total parameters are this, the trainable parameters and the non-trainable parameters. It has shown everything here. Now it is finally the time to train the model with Kera's fit function. Fit function is used to finally train the model. Now it has given the batch size, the number of epochs. We have 10 epochs right now. So let's try and run this. It will take some time to run all the epochs. Finally, we trained our model using 10 epochs. We can, try with the other epoch values like 15, 20, 30, and we can see how our accuracy and validation loss and accuracy will go. Now here, if you can see, we have achieved good accuracy of like 96%, but the validation loss is approximately equal to 0.3, that means 30%. That means it looked like the data, the model is overfitting. And overfitting gives an intuition that the network has memorized the training data very well, but it is not guaranteed to work with the unseen data. So we have different methods to overcome that. But since here we already got this well accuracy, now let's evaluate our model using the test dataset and let's see how it works. So for test evaluation, we are using the function evaluate, where we are providing the test dataset X and one hot input value of test dataset Y. Now, finally, to get the answer, let's just see the test loss and the test accuracy. So if we see the test loss is around 31% and 90% of the test accuracy. Now, test accuracy looks impressive. It turns out that our classifier does better than the benchmarks that were reported. So the benchmarks for SVM classifier on this dataset has the accuracy of approximately 89%. So we see that using CNN, it has vastly improved the accuracy over the same dataset. Okay, so let's put our model evaluation into perspective and plot the, say, accuracy and the loss plots between training and the validation data. So for that, we are using Matplotlib to plot these two graphs. Okay, so here we have to give the word accuracy in the updated models of CNN. In Keras, they are expecting the keywords accuracy and the. Okay. Now, from the above two plots, we can see that the validation accuracy, see here it approximately becomes stagnant after 4 or 5 epochs, and it rarely increased at the certain epochs, right? So in the beginning, the validation accuracy was linearly increasing with the loss, but then it did not increase much. It has become some stagnant. The validation loss also shows that it is the sign of overfitting, similar to the validation accuracy. It linearly decreased, but after 4 or 5 epochs here, it started to increase. This means that the model tried to memorize the data and succeeded. So we can always, go and encounter this overfitting problem using the dropout layer in the network, but that is the discussion of another lecture. So I think this is it about for today. This is how we can implement CNN for image classification, and it is quite simple to create a network for CNN since we have the functions already created in Keras. So finally, thank you for bearing with me. If you like this tutorial, please like and subscribe Naukri Learning for more such videos. And thank you very much. Bye-bye.